right. Let's see, we're going to start on resistors in series and parallel today. We'll probably make it through these. I'm just going to write down all the rules for resistors in series and in parallel. I'll write them again as we go through them, but just sort of so you have them all together in one place. So for series resistors, you have these rules. The equivalent resistance is R1 plus R2 plus however many resistors you have in series. Now notice this is different for capacitors, that it's that inverse thing for capacitors. For resistors in series, they have the same current. For resistors in series, the voltage is equal to the sum of the voltages. We've already seen that with the loop rule. That's basically just a restating of the loop rule. Excuse me. The sum of all the voltages is equal to 0. And so if you wanted to write this as the loop rule, you could. I'll write it over here. That is that the sum of the voltages is equal to 0. That's the loop rule. Or V minus V1 minus V2 minus however many resistors you have, that's equal to 0. Where V is the voltage across the battery, or the total voltage across all the resistors in series. And then finally, V equals IR. That's Ohm's law. And then for parallel, which we'll get to soon, the equivalent resistance is 1 over R1 plus 1 over R2 plus ... However many resistors you have. Notice this is like capacitors in series. So we've seen these expressions before for capacitance. They're just flip-flop. Resistors in parallel have the same voltage. That was the same for capacitors in parallel. For resistors in parallel, the current, the total current, is equal to I1 plus I2 plus however many branches you have. So that says that if I have resistors in parallel, this current, the current going into a junction, is equal to I1, I2, I3. It splits up into 3 different currents, and they have to all add up to equal the total current going in. And then finally, V equals IR. So that holds true for each individual resistor. Now, for resistors in parallel, for series, this is what it looks like when you're in series. This should seem obvious to you here that these two are in series, but we'll see some later where they're in series, but it might not be obvious to you. The way you tell if a resistor is in series is if there are no junctions. So when you're looking at these circuits, you want to look at them and ask yourself, are there any junctions? Notice that I could also write a resistor right here, and that one would also be in series. Even though you have that bend in the circuit, there's no junction in the circuit. So again, this should seem obvious that these two are in series. They come one after the other, but we'll see some circuits later where it's not so obvious. You just want to look for the junctions, and that'll key into whether you have a series circuit or you have a parallel circuit. So, taking just these two resistors, our change in our potential is equal to I times R1 plus I times R2. Notice that whatever current I have coming off of the battery, I also have going here, and I have going here. Because they're all on a line. If a current goes through one resistor, it has to continue going through the next resistor. All right, so I have this, which is just due to the loop rule, that I have this positive change in potential, and then I have negative changes in potential, so that if I add them up, I can get this expression. I can rewrite this as delta V is equal to I times R1 plus R2. And so this is where I get my equivalent resistance. This is I times R equivalent. So my R equivalent, as I wrote up top there, is equal to R1 plus R2. Plus, if I have more resistors, I just add them up. All right, so our equivalent resistance is R1 plus R2. Notice that the equivalent resistor, watch out, it'll blow your mind, that it's always bigger than any individual resistor. All right, that should be obvious too, that if I have an equivalent resistance, it's bigger than any of the individual resistors. But when we have resistors in parallel, we'll see something that's not so obvious, is that the equivalent resistor is smaller than the smallest resistor. So I just sort of write this here to keep this in mind, that we have this difference between resistors in series and resistors in parallel. The equivalent for resistors in series is going to be bigger than any individual resistor. So some other rules, I've already written these up top, but let's just write them again. Resistors in series have the same what? Voltage or current? They have the same current. It's like a pipe, right? And if you have a fluid flowing through that pipe at a certain rate, it flows through that pipe at the same rate all throughout. So resistors in series have the same current. And then also the loop rule, which says that the change in potential across the resistors in series adds to equal the change in potential across the battery. Or as we wrote up top, is delta V is equal to V1 plus V2 plus whatever other resistors I have. So let's look at these two light bulbs. If I remove R2, what's going to happen? I have these two light bulbs in series. If I take one of them out, what's going to happen to the circuit? Right, you'll break the circuit. I'm sorry, what did you say, Emma? You're right, so the other light bulb will go out. They used to have these Christmas light bulbs that were in series. You might have seen these where if you take one of the light bulbs out, then the entire strand goes out. And then you have to go and you have to find the light bulb that is actually out in order to fix it. These days, they're designed a little bit differently. Sometimes they're in series, or sometimes they have like this extra little path for the electricity to go if your light bulb goes out. It's not terribly important. So if R2 is removed in a series circuit, the entire circuit goes out. We'll see later that this is one of the reasons that our households are laid out in parallel. There's another very important reason, but what if you take out R2 and you replace it with a wire? That is, I just get rid of R2 and I reconnect that circuit. What will happen to R1? Will R1 be, you'll do this with your clicker, will it be brighter? Will it be dimmer? Or C, will it go out? Will R1 be brighter, dimmer, or go out? All right, so a few more seconds. Stop at 22. All right, A is right. It will get brighter. I have a voltage here, the voltage across the battery, and then I have V1, and then I have V2. I know that delta V is equal to V1 plus V2. So if I get rid of V2, that means that voltage 1 will go up because my delta V of the battery remains constant. All right, so my V1 is A, it gets brighter. That bulb actually gets brighter. Those of you in lab, you played with the little Christmas light bulbs, and you found that when you had 2 or 3 light bulbs in series, if you decrease the number, then the light bulbs actually got brighter. Let's see, why did the little boy eat his homework? Did I tell you all this one? No? Why did the little boy eat his homework? I did tell you that one. What does a lawyer wear to work? A lawsuit. All right. Let's look at this circuit. I want to know what is the equivalent resistance. I want to know the current through R1, and then I want to know the potential across each resistor. I want you to do this. I'll give you a couple minutes on your own, and then I'll catch up with you. But you know how to find the equivalent resistance. You just add those babies up. And then if you want to find the current remember the current through R1 is equal to the total current. So whatever current goes to the equivalent resistance is the current that goes through R1. And then once you know that current, you know resistors in series have the same current, and V equals IR. You can find the voltage, V equals IR, V equals IR, V equals IR. So take a couple minutes, I'll give you a head start. What's the equivalent resistance? It's 5. 2 plus 2 plus 1, or 1 plus 2 plus 2 equals 5. I'll write this down in just a minute. But what then is the current, the total current through the circuit? 2 amps. From Ohm's law, the current through the equivalent resistance, which is 5 ohms, is I equals V over R. That's 10 volts over 5 ohms, which is 2 amps. So the current through R1 is also what? 2 amps as well, because resistors in series, they have the same current. Whatever current goes through the first one has to go through the second and the third one, and that's also equal to the current through the equivalent resistance. So if I have 2 amps through this resistor, the voltage is V equals I times R. 2 times 1 are 2 volts. How about this one? What's the voltage? 4 volts and 4 volts, right. Notice I have 2, 4, and 4 volts. 2 plus 4 plus 4 equals 10. Let me write that down. So the equivalent resistance is 1 plus 2 plus 2. That's equal to 5 ohms. And so I like to redraw my circuit each time. And you'll find that it's helpful when you get to more complicated circuits. This one's not terribly complicated, so you might not need to do it. But notice that here my current, I, is equal to V over R equivalent. That's 10 volts over 5 ohms, which is 2 amps. So I got 2 amps going through here. Then the voltage across each resistor, V1 is I times R1. That's 2 amps times 1 ohm, which is 2 volts. And then in a similar way, V2 and V3 are equal to 4 volts and 4 volts. That's 2 amps times 2 ohms, 2 amps times 2 ohms. Now notice that V1 plus V2 plus V3, that's 2 plus 4 equals 10 volts. And that this value is the same as that, is equal to my change in potential across the battery. So those are the basic rules for resistors in series. You could probably look at these too, and on some combinations of resistors, you'll be able to look at them and figure out what is the distribution of voltages, just like you did for capacitors. I know that since V equals IR, a bigger resistance has a bigger voltage. So this has a bigger resistance, the same current as this one, so its voltage is going to be twice this resistor. I also know that these have to add up equal to 10. So you can think about the distribution of how those voltages are supposed to be, and you could maybe reason in your mind that they're supposed to be 2, 4, and 4, because I know that they have to add up equal to 10. It's kind of like what we do with capacitors. Now this one you might not be able to see it in your head because, I don't know, those numbers might just not come that easily to you, and that's okay. But to find the voltage, you have to find the equivalent resistance, then find the current, and then you can go back and find the voltages across each individual resistor. All right. This one's simple. We're going to do some more complicated ones where you have combinations of resistors in series and in parallel. Why don't you try this clicker question? You know what? Try just looking at it for a couple minutes. Don't use your calculator. I mean, I'm not going to use a calculator if you want, but just try just looking at it for a couple minutes and think about what should be the relative distribution of voltages. Like there's one answer here that you can just get rid of right away. Which one is that? The 16, because I know that any one resistor can't have 16 volts because I only got 12 volts going to them. So see if you can identify the right answer. We're doing pretty well so far. In fact, only one of you has a wrong answer. A couple of you. Ask your neighbor if you like and see what they put. They probably have the right answer. All right, so a few more seconds. Stop at 116. Okay, good. B is right. 4 volts. I'll show you how to work it out sort of the long way, but let's look at it and think about how the voltages are distributed. It says 16 just isn't reasonable. Can't do 16. But I know that this voltage has to be twice this voltage. And then I also know that this voltage has to be 1/3 this voltage because of how the resistors are distributed. And so, you know, I'm thinking probably 4 because it's sort of a middling number. So let's think 4 first. If this is 4 volts, this will be what voltage? 2 volts. And if this is 2 volts, then this is going to be 6 volts. So I got 2, 4, 6. 2 plus 4, that's 6. Plus 6, that's 12. Is what I got here. So you can think about your voltages and how they're distributed and often come up with the right answer without ever writing anything. But let's go through the longer process. The longer process here is to find the equivalent resistance. 4 plus 8 plus 12. And that's equal to 24 ohms. Then the current is V over R equivalent. That is equal to 12 over 24, or 0.5 amps. And then I know that I have 0.5 amps here, 0.5 amps here, and 0.5 amps here. To find the voltage, V equals IR, will be a half of 4, which is 2 volts, a half of 8, which is 4 volts, and a half of 12, which is 6 volts. And then I can just double check these to make sure that they all add up equal to 12, which they do. These two numbers are equal. By the way, you don't have to have a battery per se. As we'll look at other circuits, we'll see that there are series circuits embedded within other circuits. Really all I'm concerned about is that between this point and this point, I have a potential difference of 12 volts. That doesn't make sense to you. Don't worry, it will later when we see those combination circuits. But for now, just sort of keep that in the reserve, that I can have a battery, or I can think of this series circuit embedded within another circuit. Okay? Is that too much for Monday morning after daylight savings time? Circuits are kind of fun, actually. I find that some students really like circuits because they're sort of, like we said with capacitor circuits, they're sort of like a puzzle. And the rules aren't complicated, but you sort of have to see how all the rules fit together on a given circuit. Let's look at parallel circuits. Actually, before we do that, let me show you something. This is very important. The Chem Club is having a fundraiser of sorts for Pi Day. Pi Day is tomorrow, March 3.14, right, March 14th. And they're having a fundraiser. The Chem Club, you know, like the food that y'all had when you met with the folks over here, that's Chem Club. These various events that we've had, where they make ice cream and stuff like that. That's all Chem Club stuff, and those things cost money. And so they're having a fundraiser where they're going to pie your favorite or least favorite, I think, professor in the face. And the way that we choose that person is that you can donate money to the Chem Club. You give it to Christy in the main office. That's right over there. And there are 3 people, me, and then Dr. P, and then Dr. Cortez. So whoever you like the most or the least, however you want to do that, you can give money to see them pied in the face. And that will be on the 17th, which I think is Friday, right? Yeah. Can you give any quantity? Yeah, you can give. You can give a quarter, or you can give like $300. All right.
Give some more money to add another professor.
No, they asked us to volunteer, so they didn't volunteer. Like, we're not looking for a grudge. Is that what you're looking for? Okay. All right. So I'll remind you again on Wednesday, but that'll close on Friday morning. Okay, so for resistors in parallel, I've already written the rules, but let's just sort of rewrite them. The potential difference across each resistor is the same. And this was the same for capacitors. It's really just the equivalent resistance and capacitance that switched, but otherwise a lot of the rules are the same. So the potential difference for each resistor is the same. The current entering a junction must equal the current leaving. And we call this the junction rule. We could write it as I in equals I out. Or if you want to write it as I, as I did before, equals I1 plus I2 plus ... I write it this way because usually in parallel circuits that we'll see, you'll only have one incoming current, but you'll have more than one outgoing current. But when we get to multi-loop circuits, you'll see that we can actually have multiple incoming currents and multiple outgoing currents. But those are the same. Our incoming is equal to the outgoing current. And then for our equivalent resistance, it's 1 over R1 plus R2 plus however many resistors you have. Just to remind you, we have some combinations that I like to use when I have resistors in parallel, or I use this for capacitors in series. Like for example, if I have a 3 and a 6, that has an equivalent of 2. If I have a 4 and a 4, that has equivalent of 2 as well. If I have 3, 3, and 3, that has an equivalent of 1, right? 1 over a third plus a third plus a third, that's equal to 1. What else we got? 5 and a 5, 1 over a fifth. 10 and a 10. Yeah, 10 and a 10. That gives me an equivalent of 1 over 2/10, 1 over a fifth. That's a 5. There was another one. It's like 3, 6, and 12, or 3, 4, and 6. Do you remember? It's 3 is... I forget. But look for those combinations as you work through the problems, because I like to use those. They just make your problems to work out easily. All right? Let's see. I wanted to recap. Can we recap those rules one more time? It helps to sort of ingrain them in your head. So for series, the equivalent is equal to R1 plus R2 plus however many. By the way, you'll probably have a couple of multiple choice questions just about the rules, just that you know the rules. You'll have to use them to do the circuits, but just that you know these various relationships. These resistors have the same current. V is equal to V1 plus V2. That's the loop rule. And then finally, V equals IR. And then for parallel, R equivalent is 1 over R1 plus 1 over R2. They have the same voltage. Remember before when we looked at capacitors, we said that this is sort of like you have a resistor hooked up to a battery, and then you come along and you hook up another resistor to that battery. It's like the resistors are independent of one another. They all see the same voltage across that battery. So they have the same voltage. The current is equal to the sum of the individual currents. And then finally, V equals IR. So notice how the rules, they sort of parallel one another. Have the same current, have the same voltage. The voltage equals the sum of the voltage, certain currents equals sum of the currents, and then our equivalents are similar but different. Let's see, let's do an example. Or no, let's do this. So what happens to the equivalent resistance of a parallel circuit as you add resistors? As you add multiple paths for the electricity to flow in a parallel circuit, what happens to the equivalent resistance? Okay, doing very well. Just a couple of you have an incorrect answer. So ask your neighbor what they put. It's not obvious what the answer should be, but I will stop at 53. Just a few more seconds. All right, the equivalent resistance does decrease. You can think about this in a couple of ways. First, you can think of it in terms of just numbers. Let's say that I have a 3 and a 3 in parallel. That would be 1 over a third plus a third. That's 1 over 2/3, which is 3 halves. So the equivalent of a 3 and a 3 is 3 halves of an ohm. But if I have a 3 and a 3 and a 3 in parallel, then that equivalent is 1 over 3 plus 1 over 3 plus 1 over 3. And that's equal to 1. So notice that when I added a resistor, my equivalent went from 1.5 ohms to just 1 ohm. That doesn't make intuitive sense necessarily, but if you think about my resistors and how they're laid out, you get an electron that comes along here. It travels up to this junction, and then it sees an equivalent resistance that's equivalent to these three. In fact, the equivalent resistance drives how much current comes off of this battery. But if you add an extra resistor up here, the electron comes along and it sees more paths for it to flow through. Regardless of the resistance that you've added, whether it's a big or a small resistor, the electron just says, ooh, I have another way to go. And so therefore, it's a little bit easier. Even if you put like a 1,000,000 ohm resistor right here, the electron comes along and says, oh, now I used to have 3 paths, now I have 4 paths. And so it makes it a little easier for the electrons to get through the circuit because you've added this extra little path. All right. So as I add more and more resistors, the equivalent resistance will decrease. All right. So, do you know what the best thing about Switzerland is? I don't know, but the flag, it's a big plus. Do y'all know what the Switzerland flag looks like? Okay, it's a big plus sign. Okay, so the equivalent resistance, I said this before, is always smaller than the smallest resistor. So notice here I had 2 3s, the equivalent was less than 3. Here I had 3 3s, the equivalent is less than 1. If I have a 3 and a 6 in parallel, what's the equivalent of that? A 3 and a 6 ohm resistor in parallel. 2. The equivalent will always be smaller than the smallest resistor. The equivalent will always be smaller than the smallest resistor because the electron comes along and it says, oh, I see a 3 ohm resistor. Oh, but I also see a 6 ohm resistor. And so the equivalent will be smaller than that smallest resistor because you have multiple paths for the electricity to flow. All right, I'll do this example. This one's pretty straightforward, but I want you to find the current and voltage for each resistor, find the total current, and find the equivalent resistance. A couple ways you could do this. Probably the easiest way is to recognize what is the voltage on each resistor, then calculate the current for each resistor, and then backtrack and find the total current, and then you can find the equivalent resistance. I'll show you later, but there are 2 ways to do that. Another minute, and then I'll show you on the board how to do this. I'll show you 2 different ways to do it, actually. All right. Easiest way to do this, y'all, is say I have 10 volts here and 10 volts here. I have 10 volts because I have 10 volts here. And resistors in parallel, they have the same voltage. So I have 10 and 10. And therefore, I have I1 is V over R. That's 10 over 2, or 5 amps. I2 is 10 over 4, which is 5 halves amps, or 2.5 amps. And then I is equal to I1 plus I2, which is equal to 7.5 amps. And then if I want to find the R equivalent, well, R equivalent has to be V over I, which is 10 over 7.5, which is, what is that? It's 4/3 or something, am I right? Yeah, 4/3, or 1.33. 4/3 amps, or 4/3 ohms, excuse me. That's probably the easiest way. Let me show you a just as valid way. Is at first you can find the equivalent resistance. The equivalent resistance is 1 over a half plus a fourth. That's 1 over 2/4 plus a fourth, which is 3/4, which works out to be 4/3 ohms. Notice this jives with what I found by Ohm's law. The equivalent resistance is the voltage over the total current. Then I can find the total current, which is going to be V over R equivalent. That's from Ohm's law. That's 10 over 4/3. So that's 30 over 4, 15 over 2, which is 7.5 amps. Notice this is consistent with what I found before by using the junction rule instead of using Ohm's law. And then, well, you really just have to recognize that you get 10 volts here and here to say that the voltages V1 and V2 are 10 volts. So a couple of different ways you could do that. It doesn't really matter how you do it, but it's good in circuits to be able to think about them from different perspectives. It just helps you to check your answers as you go along. Let's look at some other stuff here. Let's try this clicker question. What happens to the voltage in each resistor as you add resistors in parallel? Okay, doing really well. Just a few more seconds. I'm going to stop at 32. Okay, that's good. C is right. The voltage will stay the same. As I add more and more resistors, the voltage across each resistor will remain the same. So if I have 10 volts here, I'm always going to have 10 volts here, 10 volts here, 10 volts here, and 10 volts here. No matter how many resistors I have, I'll still have the same voltage because resistors in parallel, they have the same voltage. And resistors in parallel, they don't split up voltages like resistors in series. Instead, they share the same voltage, which is the same as the battery. All right? We'll see that, but that's a very important idea when it comes to our household circuits, which we'll do at the end of this chapter, that our houses are laid out in parallel, not just because if you remove something, the rest of the circuit doesn't go out, but mainly it's because I have a circuit where the voltage is always 120 volts, no matter how many other things I have laid out on a circuit. Now, if I have a lot of resistors, each of them draws a certain amount of current. So as I add more and more resistors, the current is going to increase coming off the battery. But each resistor will still have the same voltage. Helium walks into a bar, and the bartender says, "Hey, we don't serve noble gases here." Helium doesn't react. Come on, chemists, that was for y'all. Been saving that all semester just for my chemists. All right, let's. What happens to the total current if you add a resistor right here? If you add this resistor, what happens to the total current? Let's do it as a clicker question. Does the total current increase? Does the total current decrease? Or does the total current stay the same? If I add this resistor right here, what happens to the total current? The total current is the current right here. All right, let's stop at. I'll ask your neighbor what they put. Okay, still about a third of you have the wrong answer. So ask your neighbor what they put, please, and see if they're different from you. And if they are different from you, just take your book and whack them on the head. No, don't do that. Not good. Not productive. All right. Okay, that's a little better. I'm going to stop at 123. 123. Okay, good. A is right. What happens here? If I add this resistor, what happens to this branch, the equivalent resistance of this branch? Because when I add resistors in parallel, the equivalent resistance does what? Increases or decreases? it goes down. The electron comes along and says, hey, I have an extra path to go. It's easier for me to make it through this parallel branch because I got this extra resistor. Adding this extra little path, even if this resistor is like 1,000,000 ohms, makes it a little bit easier for the electron to navigate through this path with all these different routes it can go. So this causes the equivalent resistance to decrease, which causes the overall equivalent resistance to decrease. And then this battery says, hey, now I have less resistance. I can send out more electrons. And so the current, the total current, will actually increase. That's what we put, right? Yeah, A is increase. Yeah, we're going to do a combo circuit. We'll stop there. Or not stopping. Let's do this combo circuit. But first, why did the tomato turn red? This is a little shady, okay? But why did the tomato turn red? It saw the salad dressing. Okay, so you're going to have a combination circuit. It'll be more complicated than this, and we'll get to some in the class probably next time that are similar to what you'll see on the test. But this one's a good start. Y'all had this one, I think, in your lab, one very similar to this, just with one resistor in series with two resistors in parallel. We want to know the equivalent resistance and the voltage and current for each resistor. And on your test, that's what it'll be. I'll give you a circuit, and I'll say, tell me the equivalent resistance and the voltage and current for every resistor, just like you had for capacitors. So here, we just first want to find the equivalent resistance. I start with the part that is only parallel or only series. These are two resistors in parallel, and the equivalent resistance of these two is 1 over 1 over 3 plus 1 over 6. And of course, that's equal to 2 ohms. I find it useful to redraw my circuit each time. I recommend that you do so. You might not have to by the time you get to the test, but I find it useful to do so. So these two circuits are equivalent, and then I have 1 and 2. That gives me an equivalent resistance of 3 ohms. So my equivalent resistance, Req, total, is equal to 3 ohms. Then I can find the current. So I find this current, I, it's equal to V over R. That's this was 12 volts, so that's 12 volts over 3 ohms. That's equal to 4 amps. So look, I got 4 amps coming here, 4 amps coming here. So that tells me that I1 is equal to 4 amps. Because this is in series with the battery so far. I haven't had any splits in the current yet, so I have 4 amps. Now I know here I'm going to get a split in my current, that it's going to be 4 amps, and then it's going to split into 2 pieces. Now think about, we'll write this down and we'll calculate it, but think about, how does my current split? Which resistor, the 3 or the 6 ohm, is going to get a bigger current? The smaller one, right. So the 3 ohm resistor will get a smaller, wait, no, sorry. The 3 ohm resistor has less resistance to the flow of electricity, so it will have a bigger current. And it's going to have a bigger current by a factor of 2. All right. So I'm going to have, what am I going to have? I'll have, well, it's a fraction. Let's just work it out. So if I have 4 amps here for I1, that gives me V1 equals to 4 times 1, or 4 volts. So what is going to be the voltage across this branch right here? This part of the circuit. If this is 4 volts, the voltage here is what? It's not 4. Good guess, though. It's what? It's 8 volts. Because I know 4 volts plus whatever this voltage, it has to equal this voltage. I understand why you'd say 4. But the voltages have to add up to equal to 12. So I have 8 volts on this resistor and on that resistor. Because resistors in parallel, they have the same what? Voltage. Resistors in series have the same current, but resistors in parallel have the same voltage. So I have 8 volts and 8 volts. Then I can calculate what is my current. anytime you get two values, you can find the third. I is equal to V over R. That's 8 over 6, or 4/3 amps. And this is I equals 8 over 3. Notice if I add up these two currents, 8/3 and 4/3, it will equal to 4 amps. 8/3 amp plus 4/3 amp, that's equal to 12/3 amps, which is 4 amps, which is the same as what I have going into the circuit. That's the junction rule for resistors in parallel. The ingoing current equals the sum of the outgoing currents. 4 amps equals 8/3 plus 4/3 amps. Okay, so we see all of our various rules come into play here for this combination circuit, and we'll do some more complicated ones soon. Probably not today. Need to master this type of circuit, and then we'll move to the others. So I think there's one similar to it in your homework. This one's a little more complicated. Notice the only thing that I've done here is I've added another resistor right here. Let's find the equivalent resistance of this circuit. You're going to start with the part that is either series or parallel, but only series or parallel. So, there are several things that you can start with, but what place would we start finding the equivalent? Which resistors would we start with? Right, we're going to start with R3 and R4. So you want to first find the equivalent of these two. 1 plus 2 is 3. And then you can find the equivalent of this big parallel branch, 6, 3, and 2. And then you find the equivalent of the whole thing. So moving outwards, starting with your smallest part that's either series or parallel. Sometimes you'll have multiple parts that fit that bill, and you can just start with whatever you want. But in this case, that's the only one. I'm going to redraw the circuit each time I find an equivalent. I recommend that you do the same just for now while you're learning. So we're going to give this 12 volts. I'm going to start redrawing this a little bit. Got 4 ohms, 6 ohms, 3 ohms, and 2 ohms. Now I find the equivalent of the 6, 3, and 2. It's 1 over 6 plus 1 over 3 plus 1 over 2. That's 1, 6 plus 2, 6 plus 3, 6. What does that equal to? It's equal to 1. It's 1 over 1. So that's equal to 1. That's one of those combinations. That's what I was trying to think of that I like to give. So I have a 12-volt battery with 2 resistors in series, a 4 ohm and a 1 ohm. Actually, we're going to make this 10 volts instead of 12 to make our numbers work out easier. With a 10-volt battery, and then my equivalent is going to be 5 ohms with a 10-volt battery. Now I'm going to start stepping backwards. I'm going to find the total current. I'll find the voltage across each of these, and then I'll go back and I'll look at the more complicated circuit. So my total current is 2 amps. So I have 2 amps here. What's my voltage across the 4 ohm resistor? If I have 2 amps across a 4 ohm resistor, what is my voltage? I got 8 volts here. And then I have 2 volts here. Checking, this was 4 times 2, this is 1 times 2. Well, let's just double check our answer. I have 8 and 2, that's equal to 10, as it should be. Because resistors in series, their voltages add up equal to total voltage. Now I go back up here. I know I have 8 volts, 2 amps. If I have 2 volts across this 1 ohm resistor, that means I have 2 volts here, 2 volts here, and 2 volts here. So then I can calculate the current. I is equal to V over R. Since I know 2 of these quantities, I can find the current. That is 2 over 6, that's 1/3 amp. 2 over 3, that's 2/3 amps. And 2 over 2, that's 1 amp. Let's just double check. 1/3 plus 2/3 plus 1, that's equal to 2 amps, which is what you had coming into this branch. So that's good, because for resistors in parallel, the incoming current has to equal the outgoing current. So now wrapping this up, we just write in our answers. I have 8 volts, 2 amps, 2 volts, 1/3 amp, and 2 volts, 1 amp. Now, this one's a little bit tricky. I have 2/3 amps going through this, 2/3 of an amp, going through those 2 resistors. So that means that I have V equals IR voltage across each. So I have V equals 2/3 times 1 and 2/3 times 2. So my voltages here are 2/3 volts and 4/3 volts. That's just from V equals IR. And then I can double check that 2/3 plus 4/3 is 6/3, which is 2 volts, which is what I have here. That's a little bit tricky, and you'll get the hang of that as we do more of these, and we will do some more. And there are some on your in your homework too that you should be looking at. Go ahead and start looking at the combination circuits in your homework, as well as I think there are some series in parallel. All right, we're going to do a lot more circuits in the coming weeks. Okay, y'all get the hang of it. I know. I'll see you Wednesday. Don't forget to go see Christy if you want to donate to the pie and the face business.